Dear colleagues, my name is Konstantin Morozov, and let me introduce you results of our research on development of a generalized method for constructing graph logical models of non-basic fault-tolerant multiprocessor systems via model combination. Modern systems are becoming increasingly complex and require high reliability, especially in critical applications. Failures of control systems may lead to malfunction of entire system and cause severe consequences. Therefore, such systems are often implemented using fault-tolerant multiprocessor systems, which provide both high performance and reliability. During the development of fault-tolerant multiprocessor systems, it's necessary to evaluate system reliability. Existing approaches can generally be divided into two groups. Analytical methods usually provide high accuracy, but often require a dedicated method for each specific system. Statistical methods are more universal since they require only a failure behavior model. However, the accuracy of the results depends on the number of experiments performed. Therefore, the efficiency of the corresponding models is of great importance. Graph logical models, GL models, are used to represent the failure behavior of fault-tolerant multiprocessor systems. You can see an example of GL model on this slide, on this figure. A GL model is based on undirected graph whose edges correspond to Boolean edge functions. The arguments of these functions are elements of the system state vector. System state vector is a Boolean vector whose components represent the states of the corresponding processors, where 1 denotes an operable processor and 0 denotes a failed one. If an edge function evaluates to 0, if some edge function evaluates to 0, the corresponding edge is removed from graph, and as a result, graph connectivity on some vector corresponds to system operability for corresponding state of processor, for corresponding combination of states. A connected graph represents an operable system, while a loss of connectivity of the graph of model indicates system failure. Uh, a basic systems, it's a class of systems that remain operable for all failure multiplicities that do not exceed a specified threshold and fail otherwise. There are various approaches for constructing GL models of such systems, of basic systems, have been proposed, and these approaches usually produce models based on cycle graphs. However, there are a lot of non-basic systems that are not correspond to basic. They operation depends not only on number of failed processors, but also on exact combination of failed processors. And for these systems, GL models are typically obtained by modifying basic models. As a result of this modification, the graph structure may change and become non-cycle. And in some cases, it is possible to construct GL models that represent system failure behavior only under specific conditions corresponding to particular combination of operable and failed processors. And to represent the failure behavior of entire system, such model must be combined in some way. There exists a method for combining several GL models according to specified conditions represented by Boolean expressions. However, this approach has one important limitation. All auxiliary models must be based on cycle graphs. That is, as it was said, it's not always achievable for, in general, for any model. In this case, the model can be transformed to a common cycle graph by adding vertices connected with edges having trivial edge functions of the form f equal to 1, to constant 1. It's done if necessary. For example, here we have two models. One is based on 5 vertices cycle graph. Other one is based on 6 vertices cycle graph. So we can expand the model of with 5 vertices by adding one vertex and one trivial edge function. And after that, all the models are combined into a common GL model defined on resulting cycle graph. Here we can see the model. Here models are based on the same graph structure, and the final model is also based on the same graph. And the edge functions of such model are constructed according to expression that is presented here on slide. Here is edge function corresponding edge, and here are edge functions of auxiliary these models, and here is expression corresponding to each model. So you can see that this expression includes both edge function expressions of original auxiliary models and Boolean expression corresponding to conditions, as this was said. There is also another approach that allows combination of models based on arbitrary graph structures. There is no such limitation as for previous approach. And in this case, a pair of graphs is merged through arbitrarily selected a pair of vertices. We select one vertex on one graph and other one vertex on other graph. For example, we can select this one and this one vertices, and then we merge them via this vertex into common graph. And if we have more models, we can repeat this procedure. And as a result, finally, all models will be combined into a common GL model, into a common structure. And the edge functions of resulting model are also modified slightly, and they are constructed in this specific manner with this expression. Here we take into account both the original edge function expression and the corresponding condition expression, Boolean expression, but inversed. We can see that here it's used inversion. And there is a disadvantage of this approach is that the structural complexity of resultant model is increased. We can see that graphs become more complex, and if we have more models, then graph will be more and more complex by when we apply this merging. And the objective of current work is to develop a generalized method for construction GL models of non-basic systems. And the proposed approach combines the advantages of existing methods while eliminating their limitations. In particular, it removes the restriction requiring auxiliary models to be based on cycle graphs and enables flexible graph integration, including the merging of multiple vertices and edges into common graph. And the work also formalizes the principles of model combination, of GL model combination and transformation, and also it provides a method for combining models with arbitrary graph structures under logical conditions. And the proposed approach aims to achieve compact and structurally efficient GL models while maintaining logical complexity comparing to that of existing approaches, in particular this one approach, as it will be shown on the next slide. And the proposed approach is similar to approach for cycle graphs that was described previously. And it also assumes that all GL models are defined on the same graph structure. But it is not limited to cycle graphs. It allows graphs with arbitrary structure. However, we still need to align all graphs of all auxiliary models to the same graph structure. So to align them, a set of equivalence preserving transformations is proposed. And we have the following four transformations that can be applied. The first one is that an h with a trivial h function of the form f equal to constant 0 can be added between arbitrary vertices. We select pair of vertices here, for example, these ones, and we can add an h function with trivial, an h with trivial h function f equal to 0. There is also another one transformation. There we can split an arbitrary vertex. It can be split into a pair of vertices that are connected with h with a trivial h function f equal to 1. We can see here the vertex that was split onto a pair of vertices connected with new h. And also a new vertex can be added to the graph, and it can be connected to any existing vertex by an h with a trivial h function f equal to constant 1, like here. Here is a new vertex that was connected to this vertex with h with trivial function f equal to 1. And finally, any h, for example, this one, can be split onto a pair of edges by introducing an additional vertex. And as a result, we have two edges, one of which uses the original h function, for example, this one, and other one uses the trivial h function f equal to 1. It's possible to swap these functions. For example, this one can use original function, and this one can use trivial function if f equal to 1. There is no matter which one will be selected as trivial and which one will preserve the old original function. And in work, it's also shown that these transformations are sufficient to align graphs of arbitrary GL models to a common structure. And the algorithm was proposed that is based on the proposed method, and it allows to construct a GL model of an fault-tolerant multiprocessor system whose failure behavior under set of conditions that are denoted as C1, C2, and up to CK, which are correspond to given GL models denoted as M1, M2, up to MK. So first, if it's necessary, the conditions are transformed so that exactly one condition holds for any system state. And then the corresponding Boolean expressions for each condition are constructed. These expressions are based on system state vector values. After that, the auxiliary models are transformed into equivalent models defined on the same structure graph G. Using the proposed in this paper equivalence preserving transformation. And the H functions of the resulting model are then constructed according to the expression presented on this slide. This one, it's the same expression that was used in the approach for cycle graphs combination. And as a result, the obtained GL model defined on that graph G that was obtained by these transformations represents the failure behavior of the system under all specified conditions. So let's consider an example, a fault-tolerant multiprocessor system consisting of 8 processors, and the system is resilient to all failure configurations with multiplicity not exceeding 2. And in addition, it is resilient to 22 failures configurations of multiplicity of 3, corresponding to set of system state vectors presented on this slide. You can see them here. So first we can construct the GL model presented on this slide. It's modeling its edge functions. It's built with some one of existing approaches. And this model represents a system that is tolerant to all failures of multiplicity not exceeding 2, as well as to the following 8 failures that are represented by these vectors that are of multiplicity of 3. And here is presented a condition expression. We can see that it corresponds to all these 8 vectors because each of them contains a value equal to 1 in both 6th and 7th positions. We can see that all of them contain 1. So we can use this condition. And similarly, we construct another GL model with other approach that is presented on this slide. And this model also represents a system that is tolerant to all failures with multiplicity not exceeding 2. However, in addition, it is tolerant to the following 14 failure configurations of multiplicity of 3. And no one of these vectors contains value equal to 1 in both 6 and 7 positions, only on one of them, not on both. And therefore, the presented condition expression that is here corresponds to them. And in addition, we can see that among the conditions C1 and C2, I mean this one and this one, exactly one is always true for any system state. So we can also see that the union of these sets of vectors, this one and this one, exactly corresponds to a considered system. It means that to this set of 22 vectors. So combining both models allows us to construct GL model of the system. And both models can be transformed in the presented way to obtain a common graph structure. It's modified model 1, and here is modified model 2 with adding some or splitting some vertices by adding some edges and so on. We can do it and we can obtain common structure. And as a result, the combined GL model is also presented on this slide. It's presented here. And alternatively, the transformations can be performed in different way, like here. We can see it. And we can also combine these models. And as a result, the graph of the resulting model is slightly simpler. It contains one fewer edge. We can compare them, but they both represent the same system. And we can also use the existing approach based on graph merging for this system. And resulting model is presented here on the left side of the slide. However, when we build this model, we can see that some edge functions of this model become trivial, in particular f equal to 1. And due to this, the model can be optimized. Some vertices and some edges can be removed. And the optimized model is shown on this right side of the slide. However, both resulting graphs are significantly more complex compared to models obtained using the proposed approach. Means this one and this one. And the table, this table presents a complexity comparison between the models constructed using the proposed method and the existing method based on graph merging. We can see that the proposed method makes it possible to obtain graphs with lower structural complexity, that is, with fewer number of vertices and edges. And compared to existing approach, this one, And at the same time, the logical complexity measured by a number of logical operators in edge functions remains comparable for both approaches. We can see it here. So in conclusion, a generalized method for construction GL models through the combination of auxiliary models has been proposed. The approach removes restrictions on graph structure and enables a unified modeling framework. In addition, equivalence-preserving transformations are introduced to align different models to a common graph structure. And the proposed method has been validated through analytical and exhaustive verification. It has been demonstrated that identical failure behavior can be represented by GL models with different graph structures. At the same time, improved structural efficiency is achieved while maintaining comparable or even lower logical complexity. And future work may include broader validation of the proposed approach and further optimization of model construction methods. Thank you for your attention.